Welcome back to Mechanical Engineering Made Simple. Today we are wading into a topic that is deceptively quiet. It's a field where if everything is working correctly, absolutely nothing moves. But if you get the math wrong, you don't just get motion, you get catastrophe. We are talking about keeping dams from bursting, ships from capsizing, and, high-pressure pipes from ripping open like paper.
That's right. We are doing a deep dive into fluid statics.
Now, statics usually implies the boring part of the curriculum for a lot of engineering students. Forces in equilibrium, no acceleration, no velocity vectors to chase.
Right.
But looking at the source material we've pulled for this, a really comprehensive technical text on fluid mechanics, it is clear that static does not mean powerless.
Far from it. Fluid statics is simply the study of fluids where there's no relative motion between the fluid layers. That's the technical definition. But in practice, it is the study of potential energy just waiting to be released. Whether that fluid is the ocean pushing against a submarine hull at crush depth or hydraulic fluid just sitting in a brake line, the physics dictates whether your structure holds up or fails.
And the stakes are obviously very high. So let's unpack this. We're going to cover pressure characteristics, how we actually measure these invisible forces, the eureka moment of buoyancy, and the geometry that keeps ships upright in a storm.
And we will finish with a weird edge case. Fluids that are moving but are, well, mathematically considered static.
Which still hurts my brain a little, but we will get there. Let's start at the absolute bottom, or rather the fundamental definition. We throw the word pressure around a lot, but in an engineering context, what are we actually saying?
It is surprisingly clean. The source text defines average pressure with a very simple relationship. It's just force divided by area, P equals P over A.
Force over area. And this distinction is vital because a massive force spread over a massive area might result in very low pressure. But a tiny force on, say, a needle point.
Infinite pressure, theoretically. This relationship is the cornerstone of everything else we are going to discuss. It explains why a sharp knife cuts and a dull one doesn't.
Same force, smaller area, higher pressure.
Exactly. And this leads us directly to the first major figure in our deep dive, Blaise Pascal.
The source material actually includes a bio on him, and the guy was a prodigy. It says he invented an arithmetic computer at age 19.
Wow.
I think at 19, I was still trying to figure out to do my own laundry.
He was definitely operating on a different level. And because of his contributions, the SI unit for pressure is named the Pascal, 1 Newton per square meter. But beyond the unit, his lasting legacy here is Pascal's law.
Okay, lay it on us. What is the law?
Pascal's law states that the intensity of pressure at any point in a fluid at rest is the same in all directions. More importantly, if you apply pressure to a fluid in a closed vessel, that pressure is transmitted equally to every single part of that fluid. It doesn't diminish.
And this is the cheat code behind hydraulic machinery, isn't it?
It is.
The text has a diagram of a hydraulic press. It shows how we can lift a car with just a human hand. It feels like magic, but it's just physics.
It comes right back to that force divided by area definition. Imagine you have two pistons connected by a fluid-filled pipe. Piston 1 is tiny, let's say 1 square inch. Piston 2 is massive, 100 square inches.
Okay, I'm visualizing it.
If I push down on the small piston with 10 pounds of force, I create a pressure of 10 psi. Pascal's law says that 10 psi travels instantly to the big piston.
So the big piston also sees 10 psi.
Exactly. But here's the trick. Since force equals pressure times area, you take that 10 psi and multiply it by the 100 square inches of the big piston, and that gives you 1,000 pounds of lifting force.
You put in 10 pounds, you get out 1,000. That is a 100-to-1 mechanical advantage.
The math is clear. The second force equals the first force multiplied by the ratio of the second area to the first area. It is why you can stop a 2-ton car just by twitching your foot on the brake pedal.
It's all about leveraging the incompressibility of the liquid. Now, that covers fluids trapped in a box. But most of the time, engineers deal with fluids out in the wild. Oceans, reservoirs, the atmosphere. The source moves on to pressure of a fluid at rest regarding depth.
Right. This is where we leave Pascal's closed container and look at the vertical column. In a fluid at rest, pressure varies directly with depth. The text derives this by balancing the forces on a tiny theoretical element of fluid. The resulting formula is P equals P naught plus rho r AGH.
Okay, let's translate that into English.
Pressure equals the surface pressure plus density times gravity times height.
Or depth, in this case.
Or depth, right.
Right.
Rho RAG is also known as the specific weight of the fluid. Basically, the deeper you go, the more water is sitting on top of your head.
It's a linear relationship. So if you dive down 10 meters, you add a certain amount of pressure. Go down 20 meters, you've added double that amount.
Precisely. This is why submersible hulls have to be so incredibly thick. They aren't just resisting the water around them, they are carrying the weight of the entire water column above them. And this brings up an important distinction the text makes between absolute pressure and gauge pressure.
I feel like this trips up a lot of students.
It does. It is all about where you set your zero. Absolute pressure sets zero at a perfect vacuum-empty space, no molecules, nothing.
Whereas gauge pressure sets zero at whatever the current atmospheric pressure is.
Right. Because we live at the bottom of an ocean of air, we are constantly under about 14.7 psi of pressure. But we don't feel it. We are equalized to it. So for most engineering applications, like checking your tire pressure, we don't care about the atmosphere. We only care about the pressure difference.
So if my tire gauge says 30 psi, that is 30 psi above the outside air.
Correct. If you wanted the absolute pressure inside that tire, you would have to add the atmospheric pressure to your gauge reading. The formula is just gauge pressure equals absolute pressure minus atmospheric pressure.
And the text notes that this can go negative.
Yes. If the pressure is lower than the atmosphere, we have a vacuum pressure or negative gauge pressure.
So we know what pressure is, and we know how to calculate it based on depth. But how do we physically see it? The source details a few devices, starting with the manometer.
The manometer is the simplest application of that ρGH formula. It's usually a U-shaped glass tube. You put a heavy liquid in it. Mercury was the standard for a long time due to its density, though we avoid it now.
You hook one end of the tube to your pressure source, leave the other open to the air, and just see how far the liquid moves.
It is elegant because it is undeniable. If the liquid is pushed down on one side and rises on the other, you just measure the difference in height. Let's call it h. The pressure difference is simply the density of that liquid times gravity times h. No calibration needed, really. It is just gravity and mass.
But glass tubes are fragile, and mercury is dangerous, so the text highlights a more robust industrial standard, the Bourdon tube.
If you walk into any factory or look at an air compressor in a garage, that round dial gauge is likely a Bourdon tube. It was invented in the 19th century and hasn't really changed because it works so well.
How does it work internally? It just looks like a cloud mechanism from the outside.
It is actually a deformation mechanic. Inside the casing, there is a curved metal tube. Imagine a party horn that curls up. The key is the cross-section of that tube. It isn't a perfect circle. It is elliptical or flattened.
Okay, so it is an oval tube bent into a C shape.
Right. When you pump pressure into it, the fluid tries to push the walls of the tube out to make the cross-section circular. A circle holds more volume than an oval for the same perimeter. As the tube inflates and tries to become round, it physically straightens out.
It uncurls.
So slightly. That tiny uncurling motion is linked mechanically to the needle on the face. So you are seeing the elastic deformation of the metal calibrated to read as pressure.
That is a brilliant piece of mechanical design. No electricity, just geometry and material properties. Speaking of geometry, let's scale up. We're moving from gauges to civil engineering, dams, and sluice gates.
This is where the math gets critical for safety.
Right. The challenge is calculating the force of water pushing against a vertical wall. Now, my intuition, and I suspect the intuition of many listeners, would be to find the area of the wall, find the average pressure, and assume that force acts right in the middle, the geometric center or the centroid.
And if you built your dam based on that assumption, it would likely fail.
Comforting. So why isn't it in the middle?
Think back to what we just said. Pressure isn't constant. It gets higher the deeper you go. So near the surface, the push against the wall is gentle. At the bottom, the push is massive.
So the average dot isn't in the middle. It is weighted towards the bottom.
Correct. The text distinguishes between G, the geometric centroid, and C, the center of pressure. The center of pressure is always below the centroid.
The text actually gives a specific formula to find exactly where that point is. It involves the moment of inertia.
It does. It shows that the deeper the water, the closer those 2 points get. But they never quite touch. The center of pressure is deeper than the centroid by a factor related to the shape's inertia divided by the depth times area.
We don't need to memorize the derivation, but the implication is what matters. Why does this offset matter for a generic engineer?
Torque. If you are designing a hinge for a gate or calculating the tipping moment for a concrete dam, you need to know exactly where the force is pushing. If you assume it's in the middle, you will underestimate the leverage the water has to tip your wall over.
So it's like the water is pushing low, effectively trying to sweep the legs out from under the dam.
That is a vivid image, but yeah, that's exactly it. Sweeping the legs.
While we are talking about structural failure, the text brings up hoop stress.
This is the force trying to tear a cylinder apart. Think of a pipe carrying high-pressure steam, or even a soda can. The pressure is pushing outwards in all directions.
The question is, how strong does the wall need to be?
The formula derived is T equals PD over 2.
Okay, so tension equals pressure times diameter divided by 2.
Right. T being the force per unit length of the pipe wall. Notice that D for diameter is in the numerator. That means if you double the diameter of your pipe, you double the tearing force on the walls, even if the pressure stays the same.
That seems counterintuitive. 100 psi is 100 psi, right?
True, but in a wider pipe, that 100 psi is acting over a much larger internal surface area, creating a larger total force that the material has to hold together.
Ah, okay. That is why a small copper tube can have thin walls, but a massive municipal water main needs thick steel or concrete reinforcement.
You've got it.
So we have covered pushing down with depth, pushing sideways on dams, and pushing out on pipes. Now for the classic, pushing up, buoyancy.
Archimedes.
The source calls him the greatest engineer of ancient Greece. Apparently, he also invented a planetarium.
He was a polymath. But his principle of buoyancy is the headline here. It states that the buoyant force on a submerged body is equal to the weight of the fluid that body displaces. The formula is F equals rho OGV.
Density times gravity times volume. This explains why a steel ship floats. It isn't about the material, it is about the volume of water it shoves out of the way.
Exactly. As long as the weight of the water you displace is greater than the weight of the ship itself, you float. But floating is only half the battle. You also have to stay right side up.
This leads us to the section on stability, which I found to be the most complex part of the text. We have a soup of letters here, G, C, and M.
It is complex, but it is visual. Let's break it down. You have G, the center of gravity. That is the point where the ship's weight pulls down.
Okay, usually somewhere in the middle of the ship.
Then you have C, the center of buoyancy. That is the geometric center of the underwater part of the hull. That is where the water pushes up.
So when the ship is sitting perfectly flat in calm water, G and C are lined up vertically. Downward pull, upward push, balanced.
Right. Now imagine a wave hits and tilts the ship to the right. The center of gravity, G, doesn't move relative to the ship, assuming the cargo is strapped down properly. But the shape of the underwater hull does change.
Because the right side dips into the water and the left side lifts out.
Exactly. So the center of that submerged volume shifts to the right. The center of buoyancy, C, moves to a new spot. Let's call it C prime.
So now the upward push is offset.
And that offset is everything. If you draw a vertical line straight up from that new buoyancy point C prime, it will cross the ship's center line at a specific point. That intersection point is M, the metacenter.
The metacenter. It sounds like a comic book location, but I gather it's important.
It is the most important point in naval architecture. The rule is simple. For a ship to be stable, M must be higher than G.
The metacenter must be above the center of gravity. Why?
Because if M is high, the buoyancy force and the gravity force create a lever arm, a righting moment, that twists the ship back to upright.
And if M is below G?
Then the lever arm works the opposite way. It twists the ship further over. The ship capsizes.
So logically, you want M to be as high as possible, right? You want a massive metacentric height, the distance GM, so the ship is super stable.
You would think so. And for warships, that is true. The source mentions warships have a metacentric height of around 1 meter or more. They are very hard to flip, but there is a trade-off.
What is the downside of being too stable?
It creates a stiff ship. If a wave hits, the ship snaps back to upright incredibly fast. It is violent. The period of roll is very short.
That sounds miserable for the crew.
It causes seasickness, fatigue, and makes it hard to operate equipment. Now compare that to a cruise ship. The text says large passenger ships have a much lower metacentric height, maybe 0.3 meters.
That seems risky.
It is safe, but just barely. The lower GM means the restoring force is gentler. When a wave hits, the ship rolls slowly and returns to upright slowly. It is a tender ship, much more comfortable for the passengers at the buffet.
That is a fascinating engineering compromise. You are tuning the physics for human comfort versus ultimate survivability.
Engineering is always about trade-offs. You can't have everything.
All right, we are in the home stretch. We have been talking about fluids at rest, but the text throws a curveball at the end, moving fluids that are technically static.
It is referred to as relative equilibrium.
Which implies the fluid isn't moving relative to its container.
Exactly. Imagine you are in a car holding a cup of coffee. The car is moving at 60 miles per hour on the highway. As long as the speed is constant, the coffee is flat. It behaves exactly like it is sitting on a table.
But if the driver slams on the gas,
Linear acceleration,
okay,
because the coffee sloshes back. The surface of the liquid forms an angle. The text gives us the formula for that slope. Tan theta equals A over G.
the tangent of the angle equals the acceleration divided by gravity, so the harder you accelerate, the steeper that slope becomes.
And this isn't just about spilled coffee. If you are designing a fuel tank for a jet fighter or a rocket, you need to know where the fuel is going to be when you hit the afterburners. You don't want your fuel pump sucking air.
Right, because all the liquid is plastered against the back wall. And then there's the rotational version, the spinning bucket.
Gyrostatics. If you spin a cylinder of liquid, the surface curves, it dips in the middle and rises at the walls.
It forms a parabola.
A paraboloid of revolution, to be exact. The math is beautiful here. The height difference, z, follows the square of the angular velocity, omega. The formula is z equals omega squared times radius squared divided by 2g.
That squared term is the kicker. If you spin it twice as fast, the height difference gets 4 times larger.
Right. This is the principle behind centrifuges. You can generate artificial gravity at the outer walls that is thousands of times stronger than Earth's gravity. It allows us to separate blood cells, enrich uranium, or separate cream from milk.
It is amazing how we started with water in a glass and ended up with centrifuges and battleship stability. It really reinforces that fluid statics is everywhere.
It is the invisible infrastructure of the world.
Before we wrap up, I want to touch on the etymology note the source included. I am a sucker for word origins. We all know aqua means water,
Latin, straightforward.
but the text traces the root back much further to Sanskrit. Specifically, the word for water offered to Buddha.
Okay, that sounds very spiritual.
That route traveled west to become aqua, but it also traveled east along the Silk Road to China and then Japan. In 10th century Japanese classics, the word aka appears,
Meaning water.
meaning bilge water.
Oh, that lost a little bit of its holiness along the way.
Just a bit. But it is a reminder that whether it is holy water or bilge water, the physics are the same.
That is the beauty of it. The laws of physics don't care about the context. They just care about the variables. If you understand the variables, density, gravity, depth, you can predict the outcome.
And that is the core message here. Engineering is the art of prediction. We calculate the center of pressure so the dam holds. We calculate the metacenter so the ship rights itself. We do the math so reality doesn't surprise us.
Because in fluid mechanics, surprises usually involve getting wet or getting crushed.
A sober thought to end on. That brings us to the end of this deep dive into fluid statics. If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.